Thanks for joining until the end. I won't take away so much time from the next entry, which is the coffee break. So yes, it's true I will talk about QBM, but actually the goal of this talk is to give an overview about the activities that we did in the context of generative learning at CERN. So my background is mainly on energy physics, and I did some training during the years to get used to these new techniques. First and foremost, I want to thank the organizer and the chair for the invitation for this exciting organization of QTML. So I was asked to give a first introduction. Technically, they call it tell your grandmother how this should work. So I will give a very high-level introduction and explain what will be the talk about. So let's start with the basics. We know very well everything, but while I was preparing the slide, I realized that every time we do a kind of quick introduction of machine learning, there are some ideas and some buzzwords, I would say, that actually we use to motivate a lot of the research paper that we also discussed during the conference. So machine learning is about complex models that can design with vector matrix multiplication and nonlinear transform and achieve universal function approximation. So all of these things are something that we are trying to do, and we did during this year, and there were a lot of presentations during QTML, try to get to this kind of level of precision. And in general, machine learning is what about? Is about data, is about the fact that you have labels in the data or you don't have labels in the data, and so you have supervised or unsupervised learning. And what we do with QML is exactly the same, and the reason behind that is that many times a lot of the work that we do in QML is inspired a lot by classical techniques. And this is very important because actually we heard also in the opening talks that some of the breakthrough techniques that can come really by reading again or reading at least for the first time, maybe a paper from 10 or 15 years ago. So this is very interesting. And what we do in QML is looking into, at least for what we do in particular at CERN, is in looking into data that we can encode in quantum state. We do some adaptive search for suitable measurement operator. We know more or less everything about this, so we have very, let's say, important paper from Maria about quantum embedding, how we can use different feature map, how we can draw a decision boundary in the feature space. And I would say the most general, I would say, representation of, let's say, a variational circuit is the structure that is shown here. So you have a repetition of a parameterized unit is to encode the data, and then you interleave this with a parametric circuit of variational ansatz. So everything is quite common. Which model are we interested in here? So I was talking about supervised learning, unsupervised learning. Actually, what we would like to have is that I give you a data set, and then you provide the model to generate new data points that should follow the same distribution. So this is, let's say, a very naive definition of a generative model, right? And we do this for generate images. We do this to help Amira writing the paper on boost, on quantum boost, as she was explaining yesterday. And of course, in energy physics, we use a lot of generative models to compare what we measure at the detector with very complicated generative models. So for the detector, for the process itself. And some of the tasks that we want to achieve with a classical, at least generative model, and we hope to do the same in the quantum context, is about data generation. So there are very important applications in chemistry for molecular synthesis. Actually, there are a lot of applications I discovered in medical science about solving the inverse problem, so the measuring of plausibility of data. And I'm a bit biased here, you can do also some kind of anomaly detection. So you want to see if something strange is on your ingredients. But joking apart, the things that we know about generative model in a very general setting is that you can have explicit or implicit generative models. So explicit are the one when the explicit density form is given so that you can perform likelihood inference. You have access to QX in polynomial time, and some of the examples of the model that are under this category are autoregressive neural network, transformers, and tensor networks. In general, we are used to work mainly with implicit generative model, so no distribution is specified or required, so you have to access to the sample given by the problem that you have in real life. And then you have to apply some flexible transformation from random noise to generate the samples. And actually, this is some of the direction that also quantum generative models take. And indeed, part of the implicit model are generative model, generative adversarial model, diffusion model, and I would say the great majority of quantum generative model. And so the goal is to give you a quick overview of those models before getting to the next point. Where does quantum computer fit in? I'm still in the NISQ approach, so I will represent my quantum computer as a variation circuit. And so the idea is that in the training phase, you need to learn the target distribution. So you train your variation circuit, you generate a new sample, then you need to define your loss function, and we will discuss a little bit about that. And then once you train the model, you should have a model that is able to sample somehow efficiently the new data. Of course, this is not a technical definition. It's far from being rigorous. But if you want a real connection about learnability and complexity of generative model, I just put here a reference that I found very interesting. So what is this talk about? This talk is about building a bridge. This is a project that Italy has ongoing for many years. I don't know if it never happens, but essentially the bridge is about going from Calabria to Sicily, which is almost 3 kilometers. And for us, the bridge is about bridging from NISQ to, let's say, early fault-tolerant. And to use the bridge, I selected a couple of vehicles. We have a car and a small train. And this is because I would like to show you at least a couple of examples of the models we are looking at the moment now. So let's start the travel from NISQ to early fault-tolerant. So first of all, again, this sounds a little bit of repetition, but I need the repetition to connect the dots for some of the points that I need later on. So NISQ complication, what does it mean? So let's start with a model that more or less we have already discussed many times, quantum circuit-borne machine. Here what we have is that we exploit the simple rule of quantum mechanics, so the Born rule. I give you a variational circuit, you sample it, and then you get as output an n-dimensional binary strings. And actually this model seems to be simple, but power enough because QCBM has proven of hardness of sampling, and this is clear. And then if you like a different approach, again you take some inspiration from classical machine learning, and you use an adversarial training approach. So you have two elements here, generator and discriminator, and then you choose if you want one of the two or both, if you want to become a quantum circuit. So in the, let's say, standard approach, usually you have a quantum generator where you sample data, and the data you want to fool your discriminator that is actually a neural network. And then you train until you get to the equilibrium, and you can somehow find a good generative model. A little bit different, but something that, again, I need to have a full picture is about the possibility of using different loss function, and this will be an important point to understand one of the limitations. So here I'm just listing a few of the options that you have in your basket. You can use scale divergence, you can use, again, the adversarial approach. You can have a loss function defined in the phase space, and also you will use the maximum mean discrepancy. Last but not least, important model in the quantum context will be and is quantum Boltzmann machine. Again, I won't enter the details now, but just to give a full picture. So what happens? What we can do with this model? A lot of things, but for real life, what we can do, we can reproduce maybe something like this. So now the question is, can you name an object within this picture? No. And I mean, of course, I cannot generate this with a quantum computer, but the message here is that NISQ stands for something that works, but actually not enough for a real application, right? So of course, we can apply some error mitigation techniques. In the classical context, you can apply some denoising principle, but the message is that we have strong limitation. And the limitations are already explained before in the previous talk, but as a summary and as a, let's say, a motivation for the next step is that always variational circuit has problem in terms of scalability and trainability, and this is fundamental. And one of the most discussed, analyzed problem is barren plateau. That's true. We have different motivation and ways to approach it. But actually, BP are only the tip of the iceberg, right? Because when you train a quantum circuit, the problem is really the fact that estimating the gradients is much more costly in the end with respect to calculating the loss function. And if you're looking into the literature, there are a lot of paper that somehow has some very nice, I would say, result on the hardware. But if you read carefully the paper, nobody did the training on the hardware. They did the training with some kind of noise model. They got a model and they sampled just on the hardware side. So the fact that training on the hardware is almost prohibitive as today. So that's the point. What's next? One of the problems is the definition of loss function. And here a little bit biased because I want to advertise this work that we did in collaboration with people from EPFL. I think Emmanuel and Supanot are around here. So what we realize in this work are two things. The first is the fact that usually we talk about generative model in the context of implicit model. And we never discuss about how we can define the loss function. And actually, in this paper, we introduced this, let's say, separation between what is an explicit loss function, so something where you have to deal with a probability distribution that you build out of the data. So the more the data you have, the easier it is to build this explicit loss function. And under these categories, you have all the loss functions that are similar to KL divergence, right? So you can take KL divergence as the real guilty here. On the other side, you have implicit loss function. And the representative for implicit loss function is the maximum mean discrepancy. Which of the two works better? So naively, you can think about two different questions. If you approach a problem with an explicit loss function, you can look at the top graph here, and you can ask, is this bit string, let's say the blue one, in the data set that I have? While for the implicit one, the question is a little bit different. You're asking, is the bit string close somehow to one in the data set? And so it's clear that the first one is very difficult to obtain in the sense that it suffers from the curse of dimensionality. And actually, the elegant result in terms of, if you want, terminology, is the fact there is a mismatch between an implicit model and an explicit loss function. So actually what we realize is that an implicit model should go with this implicit loss function. And as a side result, even if it's not a side result, because actually this is something I will need to use later on, we realize that this maximum mean discrepancy can be described as a combination of expectation value of Pauli Z, for example. And this is very helpful because in the way you can define this loss function, you can also train somehow effectively a quantum circuit. Good. So NISQ doesn't work. The training cannot be done. So what are we doing here? Actually, and I'm happy because I saw a slide in previous talk that is doing the same kind of reasoning. The solution is, again, let's go back to the machine learning things. Let's analyze what we can call the model life cycle. So apart from the three elements on the top that are usually common also in quantum computing, so data preparation, model definition, you have model training and model testing, which is the inference part. Again, it's quite well known that the model training part is much more intense in terms of computational requirements. You have to apply your training, you have backpropagation techniques, and then once the model is ready, you can go to the inference phase when actually you have only the cost of technically the forward pass. And so what we realize is that you can put, let's say, the effort for the training on the classical computer and leave it the rest to the quantum one. And exactly this is where the community is going, right? And exactly what we see now in the literature is this protocols, which is let's train on classical and let's deploy on quantum. Of course, this is a very naive, let's say, definition because there are very important caveats, but there are very interesting papers that are following this kind of protocols. And why this is interesting? Because with a clear violation of copyright, let me use this title, it seems that all you need is this IQP circuit, or instantaneous quantum polynomial circuit. I'm well aware that tomorrow morning we will have another talk about this, so I won't enter into the details, but I want just to give you the overview of where the community is going. And why this is important, because this class of circuit consists of commuting gates with interval with Hadamard gates, and this family of circuit is classically efficient, is given by a classical efficient estimation of expectation value of Z. And the fact that you can train effectively on a classical computer is due to the fact that you can express the loss function. So the MMD as a mixture of expectation values. So this is an important result. So sometimes we have a lot of interesting contribution that seems to go nowhere, but actually you can reuse the result to apply in a different context. So you train on classical computer, and why you want to sample on the quantum one? Because for this circuit, the output distribution is unlikely to be simulable on a classical computer, right? For some complexity argument reasoning, this is a very powerful direction. I'm saying this because actually we are trying to follow a similar direction, but not exactly the same. So I won't talk about IQP circuit, so you can easily follow the talk tomorrow by Joseph. What I'm talking about, a couple of different directions. The first one is about Chebyshev polynomials. And the reason behind this Chebyshev polynomial is given by the fact that usually when we look into quantum circuit for generative learning, we would like to answer the following question. So the first one is how we develop an embedding that is hard to sample classically. So we are trying to follow the same direction as before. And also how to build an high-performance quantum generative model, because the usual question is why I should use a quantum computer if I can do everything with a classical one. And one of the directions that we can take is that one of the main differences, naively, between a classical computer and a quantum computer in terms of generative learning, at least, is that for a classical computer, usually you have complex integration and a reverse probability distribution to calculate, while for a quantum circuit, you need to sample out of the circuit. And so the sampling is something that you do as a projective measurement in the computational base. And so it seems that the exercise we have to do is we need to define a transformation between two bases. One is the computational basis where we sample from, and one is a convenient basis when the model has a good expressivity. So we need to define a model that for which the model expressivity is enough to represent our problem. And at the same time, we need to define the feature map that enables this sampling in the computational base. What are the ideas? So usually we are used to work in the computational basis, or for example, in the Fourier basis. And if we look into the distribution in a kind of grid sampling on those representation, we have an equidistant space within the computational base, or the clockwise representation of the Fourier one. But actually, if we look into a different polynomial transformation, for example, the Chebyshev polynomial, we see that we don't have anymore an equidistant space between the nodes. And actually, this kind of polynomial can allow to sample more efficiently on the boundaries with respect to the average sampling one. And again, this is not a new idea, right? It's just that we are trying to translate it into quantum computer. In fact, Chebyshev polynomials that are a set of complete orthogonal polynomials are already used quite often in numerical integration and interpolation. And so, again, what we do is that we try to reproduce what people have already done very well in the past. And the exercise that we want to move for the discrete Chebyshev transformation to the quantum one. So this work was initially done by the group of Alexander Kirienko from Sheffield. And actually, I'm very happy to say that this kind of, let's say, transformation and the related work has been, let's say, developed by the Penny Lane team, and this became a demo into their collection of tutorials. So in the quantum setting, the Chebyshev transformation works in this way. So we need to define this orthonormal basis, where we put the amplitudes that are the Chebyshev polynomial evaluated in the different nodes. We should guarantee the orthonormality of this basis, which has a different coefficient for indices 0 with respect to the others, like in the classical case. And then from this mathematical transformation, we need to derive what is a quantum circuit to do that. So this is what we have done together. And so, again, the idea is that this kind of transformation should allow us to have a very expressive circuit, but at the same time to work with an efficient transformation back into the computational base. And so the good direction of Chebyshev polynomial is that it leverages of quantum Fourier transform. And this is because also in the classical case, the Chebyshev transformation is related to the discrete cosine transformation that is expressed with the fast Fourier transform. So the way we do this is that we use QFT for interference and for the mixing of this cosine transformation in the quantum context. And we can write down easily a kind of a receipt about how the quantum circuit should look like. So this should contain an ancilla to restore the normalization for the different grades of the polynomial, should contain an X-parametrized isometry with a control phase feature map. We should add some permutation to reorder all the frequency obtained out of this polynomial, and then we can conclude with a multi-control rotation to guarantee that the amplitude is the end is completely real. And this is an interesting peculiarity of the quantum Chebyshev transform. So if we like this transformation that contains a quantum Fourier transform-like transformation, that's why we are trying to cross the bridge between NISQ and early fault-tolerant, we need to understand how this can be used as a generative model, because this is the goal, right? The goal is that we can train effectively this quantum circuit, okay, with a reasonable number of qubits, and then the sampling phase is obtained by reverting the quantum circuit. So we apply the transformation back with the formula that you see here in the top part. And again, this is very interesting because this is exactly what we do in general for quantum Fourier transform. So we work in a kind of reciprocal phase which is convenient for its representation, but then we need to sample from the computational base. When we realized that this can be transformed in a generative model, we contacted Alexander Kirienko and say, we have a very interesting use case to propose you, and this is how the collaboration started. So the use case that I want to use for this kind of quantum Chebyshev transformation is coming from my energy physics. And for those of you who are not familiar with these things, let's say that we want to learn a probability distribution, which is a multivariate one. Actually, it's a bivariate probability distribution that contain a series of differential equations. Actually, in physics, with this problem, you can attack the problem in two ways. Either you try to solve these complicated things, or you use a data-driven approach. So you use a generative model to solve this issue. And why this is complicated? Because it's a bivariate distribution where the two variables that are the probability of finding this parton that will produce a particle is given by two elements: the momentum of the particle and the energy scale at which this particle effect. And whatever you can find in the literature are nice 1D distribution that are calculated or obtained from the data only for a fixed energy level. So the exercise here is that we want a bivariate distribution for which I can get you the probability distribution for different energy scale. And so what we realize is that we can use the Chebyshev map formulation for the bivariate solution. And the extension to the original work is given by the fact we can put in parallel two different quantum feature map, really in parallel, and then we want to learn the entanglement structure to reproduce the correlation between those things. And so the training part works like the feature map that we showed before. So we have the encoding of the feature, Z or Q. We build our entanglement structure with a bell-like structure, and we train this variational part to reproduce the correlation among the features. After this, we are ready to sample. And the good properties of this model is that I can train with, I would say, a reasonable number of qubits, but actually the sampling stage can work with additional register. And having an additional register is a new, I would say, features, optional, that you can get out of this model, because you can increase a lot the resolution of the model itself. So here we can add additional qubit, and for every qubit that you add in the model, you can double the resolution of the problem. So that was an interesting example because we were able to train the circuit effectively, but actually you can sample with a much higher resolution. Okay, so the next topic is about quantum Boltzmann machine. So this is another direction that we are looking forward, actually together with a new postdoc that joined the team, together with another PhD student. I found this topic very interesting. It's kind of new for me because I was focusing on many other things before that. But let me say that the reason why we are looking into this is because it sounds to be a promising direction. So quantum Boltzmann machine, let's start with a very quick recap because I know there will be at least a couple of talks related to this, so I won't go into much details. So we have a general formulation of Boltzmann machine, like very interesting models that combine statistical physics and machine learning. And actually we have the definition of a restricted Boltzmann machine, which is something that makes the things trainable, or at least that makes the things easy to deal with. And this restricted Boltzmann machine is composed by two elements. You have a visible unit and a hidden unit that form a bipartite graph. And this structure is fundamental to extract some of the properties I will mention. RBM are expressive as commutative pairwise Hamiltonian and are universal approximator. Again, it's something that we are looking into classical model. The way you get information out of this model is marginalizing over the hidden variables that is giving you essentially the model distribution. And actually the calculation of the gradients for this model is kind of prohibitive, and in the literature they developed a very effective method which is called contrastive divergence, which is a biased method, but at least is a way you can train those machines. And again, the question is where we can put a quantum computer. So the easy answer would be, can I just use a quantum computer for sample this classical model? So can I do just translating of this model into an Hamiltonian sample out of it? Actually, no, this is not doable. You cannot do it because actually you have to sample from a thermal state, which still remains a very complicated thing. But while I was discussing this with the other researcher, we realized that this topic is becoming again very, very popular. And there were at least 3 papers in the recent, I would say, 2 months before preparing this talk. And one actually was published even in Nature. So there is a very strong effort from the research community to look into this topic. But the preparation of the thermal state is not, or at least is not the real problem that we have here for Boltzmann machine. And if we look into the quantum Boltzmann machine, which is a kind of extension of the classical one, when you add the non-commuting pairwise Hamiltonian, then again we realize that most of this implementation didn't succeed in practice, right? And there are some exceptions to this. For example, you can look into fully visible quantum Boltzmann machine, so you forget completely about the hidden layers. And the real problem is that we don't have, or at least we didn't have, a way to train the quantum Boltzmann machine. And the reason is given by the following. So if we think about the definition of quantum Boltzmann machine, then the way you train is that you minimize, as usual, the negative log likelihood. And if you try to explain a little bit how this is working, then you need to take the gradients of this distribution. So you have a derivative over all the parameters from the loss function. And actually what we have here is that you have to calculate many expectation value of something that is an exponentiation of a non-commuting Hamiltonian. And these terms actually can be expanded in this way. So you have a nested connection of commutator here that requires so many expectation values just for one term. And so intuitively, this is one of the reasons why we have a kind of showstopper here, because we cannot effectively do this, because you need to have so many expectation values, and for each implementation, you need to prepare a different Gibbs state. So this is very, very complicated. And so actually, this is kind of game over from the quantum Boltzmann machine, right? Because this gradient tractability stopped the progress on this topic. Actually, there are some approaches to reduce the model expressivity. For example, making non-commuting terms non-trainable. So this is a different topic, but actually, what we can do is to go back again into the real definition of how you calculate the training. And what you realize is that if you take the gradients in this way, you need to define every time a projection over the visible layer, because this is the way you get the information out of the model. And maybe what we can do is that we can define a model where we restrict the choice of these operators in a way that this operation can be simplified a little bit. And so if we take, for example, an Hamiltonian that commutes in part of the Hamiltonian that commutes with the projector operator, you realize that all of this term that we had here into this gradient calculation actually goes to 0. They are going to 0 exactly. And so what it comes out is that out of the more complicated expression that we had before, only one term is saved. Actually, this is a very nice simplification. And to do that, what we realize is that we can define, let's say, a model that stays in the middle between a full quantum restricted Boltzmann machine and the classical version. And for the sake of fantasy, we call it semi-restricted quantum Boltzmann machine. And the property of this model is that we have a commuting layer for the visible one and a non-commuting layer for the hidden units. And while we are working on this model, we realize that actually we can define a closed form for the output of the distribution from the visible layer. And by defining this closed form, we realize that we can have an expressive equivalence between what is this semi-restricted Boltzmann machine and the classical one is doing. And so what you can find out is that you have a clear relation between the dimensionality of the operator set into this semi-restricted quantum Boltzmann operation and the numbers of hidden layers that you have in the restricted one. What I mean with that? What I mean is essentially the fact that to get the same result, let's say you train a circuit to get to the same solution of the problem. And if you consider a complete set of X, Y, and Z Hamiltonian, then you need 1/3 of the parameters of the hidden layer with respect to the visible one. So you can see this from this plot, the fact that we can get to the same value of the loss function. Actually, this is a very simple numeric, so the loss function goes to 0. But with the restricted Boltzmann one, the semi-restricted Boltzmann one, you can get to this value 3 times before with respect to the other ones. And since someone this morning says that training on the hardware costs, that is to say that you can save resources to train the Boltzmann machine. This seems to be the end of the story because actually we can prove this expressive equivalence between the classical and quantum Boltzmann machine, which was kind of a new result, at least. We derived this closed expression for the analytical gradients, but actually we still don't have a way to train this machine. Despite the fact that we simplified a lot of expression, still this is very complex to obtain. And so actually this seems to be again the end of the story, but you should always repeat the same recipe. So you go back to the classical literature and you ask yourself what they were doing to simplify the gradient calculation. The answer was already there, and the answer is that they used these contrastive divergence techniques, right? So without this contrastive divergence, these have never been computationally feasible in the classical regime, in the classical literature. This contrastive divergence way of calculating the gradients is very different because it's defined as the difference of the expectation over the data. So you don't have to assess the probability distribution. So this is the turning point of the discussion. And so what is happening is that since the model distribution is a thermal state, then is approximated using what they call a k-step cycle of Gibbs sampling. And the last result from the literature is that this restricted Boltzmann machine, the conditional distribution factorize, and this is important. This is happening because we have a bipartite graph. So that's why I was mentioning this before. This is an important statement. Once you have this structure, then you can allow for an efficient classical sampling without evaluating the full thermal state. And this is a game changer, right? Because you don't have to evaluate the full thermal state. And so what we realized is that actually the solution was already there because the semi-restricted quantum Boltzmann machine admit by construction this kind of generalized contrastive divergent variant. And what we show in a very recent work is that it's possible to write these conditional probabilities over the visible and the hidden units because you can express them as a state preparation. And the state preparation is expressed by these two equations here. And actually, once you have this state preparation statement, the step you need to do is to build a quantum circuit. And so once you have this state preparation, you know that these admit the following circuit construction, with the caveat that as of today, at least for this part, we don't know what is inside, but we know what is it. And what you do here is essentially you prepare for the visible part, the visible layer, you tensor it with a maximally mixed state from the hidden part, you apply the imaginary time evolution, and then you measure the hidden part with the p-basis. For the other part, so the probability of the visible, so the conditioning on the hidden layer is given by the fact that you prepare the visible part, the hidden part, you tensor with the maximally mixed distribution from the visible, then again you apply the same time evolution, and then you measure into the z basis. Those are the two things that essentially represent the circuit of the state preparation. And so how the contrastive divergence works? So essentially, you need to build two elements to calculate the constructive divergence, what we call the positive phase, so the contribution from the visible layer, and the negative phase, which is the part that is coming from the hidden one. So this is really a cycle. So you prepare the visible, you prepare the visible part from the data with the same circuit as we've seen before, and you extract the hidden part, the conditional hidden part. This is used as an input to the next phase, which is the other circuit that I was showing before, right? So you input this into the next evolution, and here you're building the cycle between the visible and the hidden part. And actually what we know from the literature is that even if here we have a kind of cycle, so it seems that we need to repeat this sampling many times, actually most of the time k is equal to 1. So that is mean that you can just obtain 4-bit strings and you have a kind of bias, but estimation of the gradients without accessing the probability distribution. And again, what is interesting here is that these gradients can be computed effectively with this contrastive divergence. And more interesting, one of the two parts, in particular the conditional and the visible, can be done on a classical computer, so you don't even need a quantum computer, right? Because you can simply sample this in parallel with a classical computation. So what is remaining is just to define the second part on a quantum computer. And we validate, of course, this with some numerics. And I would say the most interesting result that we find out is this plot. For example, here we have 12 qubits that we train in this way. And I compare this with between contrastive divergence and the standard approach, which is the negative log likelihood. And again, in terms of budget or resource computation, here we assign different samples in terms of number to the different realization of the negative log likelihood. And you can see that the contrastive divergence in the simpler case can perform the gradient calculation with an order of magnitude less in terms of samples. And since we know that this increase with the dimensionality of the problem, we are pretty sure that this separation increase polynomially with the dimensionality of the system. Another thing that I would say is really, really exciting is that the gradient calculation now scales in this way in the forward pass, okay, because we are sampling for each update, and is scaling in the same way as the sampling cost of the quantum Boltzmann machine. And this is to say that actually we have a gradient calculation that provides a kind of backpropagation-like scaling. And I would say this was something that we were looking for a long time in the field. So what we can say, if you think about the fact that we enable the training of semi-restricted Boltzmann machine, we can also say that this is true because we don't need access to the explicit data probability distribution. And what we realize is that actually this works for the semi-restricted Boltzmann machine, but actually the contrastive divergence is a technique that can be used for other models. So the open message here is that we would like to see this method applied to different models because this will be very, very efficient. If you want the details, this is the paper. And overall, what I would say is that for us, it's important to understand how to build this bridge and how to translate between NISQ and early fault-tolerant. And one of the messages that I want to give, and this is very important because sometimes I see people discussing about variational algorithms like something that doesn't work and didn't bring anything to the field, but actually a lot of the things that now we know and a lot of the tools that we use to prove something comes from the big effort that the community put into, let's say, destroying, construct, or whatever you want to think about variational circuit. In this talk, I wanted to show you a couple of the ideas. The first one is the usage of different feature encoding for this interesting Chebyshev generative model. And the second one, we provide an interesting way to calculate the gradients for the Boltzmann machine. And before concluding, I want for sure to thank my collaborators, in particular Cenk and Maria, that are the authors, main authors of all the works about quantum Boltzmann machine, and the remaining part, which are, let's say, responsible for the discussion about the Chebyshev polynomials. And this concludes my talk, and instead of leaving you with a question, I want to leave with a kind of a reflection. I found a nice picture over a door in the theory department at CERN, and the picture was about this. And actually what I realized is that it's not a problem of the question that we ask. It's about the timing of the question, right? So what I would say is that everything that we are doing is contributing to the field. Of course, we need to align a little bit the timing with the question, but everything that we are doing is very important. And so this is about the question that people had in the 70s. They were asking if a car was better than a horse, which is a stupid question now, right? But, I mean, it's important to understand how the things evolved during the time. Thank you very much.